Hey guys, welcome to your lecture on the Bohr model of the atom and quantum theory. So we're going to take some notes on page 12 of your packet, and this is the conversation that is going to make that flame test lab make sense. So some of you had to do this lab before we had a chance to talk about this. Some of you will actually get to hear this lecture and then go see the flame test lab. So, the nature of the hybrid schedule is interesting. But hopefully this kind of puts it all in perspective for you. Okay, so what some of you have already seen in the lab is that when you heat up elements, either in the Bunsen burner flame or in the gas discharge tubes that we looked at, they emit different colors of light. And when you look at that light through a diffraction grating or a spectroscope, which were like those little pieces of plastic that we looked at, you can actually see those colors separated into all of their components. You can see the individual red, orange, yellow, green, etc. You can see those individual colors of light separated by their wavelengths. So that's kind of interesting, right? Like different elements are producing different colors of light. So much so that they're actually considered to be like unique fingerprints for the elements. These fingerprints are called atomic emission spectra, and they were first observed in 1913 by Niels Bohr. Now, Niels Bohr was actually a Danish physicist who was working in Rutherford's lab. So remember, the model of the atom we're working with right now is called the nuclear model of the atom. Remember, Rutherford's gold foil experiment determined that there was a nucleus, but they didn't know much about the electrons and where the electrons were. So, my handwriting's a little wobbly. Let me reset here. So Niels Bohr was a Danish physicist. You guys are starting to see that there's a lot of overlap here between chemistry and physics. Working with Rutherford. To determine more about electrons. They wanted to know, where are these electrons in the atom? How much energy do they have? Because remember, up to this point, we just said, well, the electrons are in that empty space outside of the nucleus, but wanted to know more about location of the electrons and how much energy those electrons had. And so in their studies, they actually noticed these atomic emission spectra. So I know I didn't exactly give you a space or a definition space for atomic emission spectra. So go ahead and maybe just write it down here underneath your Bohr model notes. Okay, these are like the elements' fingerprints. I don't know why my handwriting was so good when I set up this lecture, and now it's all wobbly. I wonder if running my recording software sort of changes how my handwriting looks. Seems odd. Okay. So the question was, why, right? They're wondering, why do certain elements only produce certain wavelengths of light? There's my lambda for wavelengths. So when we look at these atomic emission spectra that I have here, I know you guys, I only gave you hydrogen to look at in your packet, and it's not in color, so this is a lot better, being able to look at these in color. You can see hydrogen's able to produce this one red line, and then this turquoise line, and the blue, and some purples. But we look at helium, and helium produces a different wavelength of red, and it produces this yellow wavelength that hydrogen was not able to produce at all. So what the heck is going on here? Well, what they thought was happening was that because electrons and photons are both traveling as waves, they have these certain wave-like properties. If we're able to see only certain amounts of energy, then it must be the case that electrons have certain amounts of energy. So the hypothesis was that electrons have what they called quantized amounts of energy. Because if hydrogen's electron is only able to produce these specific colors, it must be because the electrons in the atom only have certain amounts of energy. Now, what they also hypothesized is that how much energy those electrons have and are able to produce depends on where those electrons are located. So electron energy depends on where the electrons, I don't know why I don't just scroll up more, give myself more room to write here. Depends on where the electrons are located in the atom with respect to the nucleus. In other words, how close or how far are they from the nucleus? So we need a new model of the atom, right? We can't just say, well, the electrons are somewhere in that empty space outside the nucleus. In order to explain these different colors of light that we're seeing, we need a new model that explains that. So go ahead and flip to your next page, page 13 in your notes. And I'm going to explain how it is that these electrons that I'm telling you have certain amounts of energy are actually producing these different colors of light that we're seeing in the atomic emission spectra. All right, so let's do that. I just realized, did I? Oh, good. I'm getting awfully close to the edge of what you guys can see here. I'm working on two screens. All right, so here is the Bohr model of the atom. Okay, so what Bohr said is, all right, Rutherford, yeah, we've got a nucleus here. So here in red is your nucleus, and this is where your protons and your neutrons are located. But instead of saying, all right, well, the electrons are somewhere outside, what Bohr decided to say is that the electrons were in these set circular-shaped orbits. Okay, so the first bullet point about the Bohr model is that the electrons exist in what we call set circular orbits around the nucleus. And he numbered those orbits according to their energy level. So the orbits are numbered as n equals 1, 2, 3, etc. From lowest energy to highest energy. So you can see here on this line, increasing energy of orbits. So the electrons that are closest to the nucleus have the lowest amount of energy, and as they move away from the nucleus, they have higher amounts of energy. These lower energy levels, where the electrons are the most stable, are called ground state electrons. When electrons are in their ground state, electrons that are closest to the nucleus and these are the most stable. And that makes sense, right? Because the negatively charged electrons are attracted to the positively charged protons in the nucleus. However, when we give these electrons, so here, right, like here's an electron in the n equals 1. When we give these electrons energy, either through heat in the Bunsen burner flame or when we electrified them in the gas discharge tubes, these electrons can move away from the nucleus. Like they can move out, for example, from the N1, maybe out to the N equals 3 energy level. We call this the excited state. And this is when elements are heated or electrified. In other words, when they gain energy, electrons move away from the nucleus. To a higher energy level. But here's the thing, you guys. Out here in the excited state at the higher energy level, they are less stable. They are unstable out here. Because remember, they're attracted to those protons in the nucleus. So when the electron is sitting out here in the higher energy level, eventually that pull of the protons is going to pull that electron back down. Now, maybe it'll fall back down to the n equals 2 energy level. Maybe it'll fall back down to the n equals 1. But it can only fall between energy levels. It can't just like hang out in between energy levels. It'll fall back down distinctly to one or the other. So like let's say that the electron falls back down. Let's say it falls down to the n equals 2. That requires some energy to be emitted, right? So if it's going from a higher energy to a lower energy, some of that energy that was absorbed has to be released. And what happens is that energy is released when the electron falls back down from a higher to lower energy level. It releases that energy in the form of a photon of light. So, I did not leave myself enough room here. When electrons fall back down, hopefully you guys have enough room, from higher, or maybe we could just say from excited state to a lower energy level, they emit that energy as a photon of light. The color of this photon is going to depend on how much energy was emitted. So notice here the energy equation that we have been working with, E equals H times frequency. We use nu for frequency. This particular image used F for frequency. So the amount of energy determines the frequency of that photon. And of course, the frequency determines the wavelength, right? C equals lambda nu. So we're going to get different wavelengths of light depending on how far that electron fell. So here, if we got if we had a transition from the n equals 2 to the n equals 1, that's going to emit one color of light. But here, where we have a transition from the n equals 3 to the n equals 2, we're going to get a different color of light. Because the distance from the n3 to the n2 is not the same distance as the n2 to the n1, even though maybe it looks that way in this particular diagram. So one of the equations that we can use to calculate how much energy is emitted, and this is for the equation in the box at the bottom of your page, the energy of the photon will be equal to the energy of the higher energy level minus the energy of the lower energy level. Ooh, that looks like lever. I don't know why I wrote an R. Level. So however much energy the third energy level has minus how much energy the second energy level has is how much energy got emitted in that photon of light. And that's how, you guys, we're seeing these different colors. Now the question is, why is it that we see different colors for different elements? Okay, and I think this goes on to your final page of notes. Let me double check the packet here. Onto page 14. Let's answer that question. So what we're trying to answer here, you guys, is like why hydrogen is able to produce, red and turquoise, but helium is able to produce this different color, red and yellow, and this green and a different turquoise. We're getting different colors for different elements. And that must be because different elements have different energy levels. Now, they're all numbered the same way. Energy level 1, energy level 2, energy level 3, all the way up to 7. But the n equals 1 is a different distance away from the nucleus in hydrogen than it is in helium. Okay, so our first bullet point to answer this question is that different elements, I think I definitely can't use two screens, you guys, when I record these because it really warps my handwriting. It's driving me crazy. Different elements have unique energy levels. For example, the n equals 1 is closer to the nucleus in helium than the n equals 1 in hydrogen. Let's think about why that's the case. Why is the N1 for helium smaller than the N1 for hydrogen? Well, think about the number of protons, right? Because that's what's pulling on those outermost electrons. Hydrogen has 1 proton. Helium has 2 protons. So when you have that additional proton in the nucleus, it's able to pull more strongly on that n equals 1 energy level, and that n equals 1 is going to be a little bit closer to the nucleus. So because these different elements have unique energy levels, and again, it's not just the N1, right? The distance from N1 to N2 and N2 to N3, these distances between the energy levels are different for every element. So there are only certain places where the electrons can exist, and there's only certain amounts of energy that they can have and transmit as they transition between those different energy levels. So, where an N2 to an N1 drop is going to produce a certain amount of energy in hydrogen, it's going to produce a different amount of energy in helium because the distance between those energy levels is different. And the other thing that's going to make all of these transitions produce different colors is every element has a unique number of electrons transitioning between all of those energy levels. So back to my hydrogen and helium example, hydrogen has just one electron making those transitions, and helium has two electrons making those transitions. So you get different amounts of electrons transitioning between different energy levels, and thus you're going to get emissions of different colors of light. How many times can I say different or unique in this one lecture? Am I driving you crazy yet? Okay. So that's what you guys were seeing in the lab, or that's what you're about to see in the lab. The bottom line is, you guys, electrons aren't just, randomly outside the nucleus. They are outside the nucleus in distinct energy levels. I mean, maybe we should write that down somewhere. I think I've hinted at it and kind of beat around the bush at it a little bit. But this Bohr model and this quantum theory, the whole idea of it is that electrons exist in specific energy levels. And they can transition between them. And transition between them. And it's in those transitions where we see those colors of light. Okay. There's one more way that we can calculate the colors of light and the energy that we're seeing when these electrons transition. So one way to do it is to use these two equations that we were talking about before, that we used in the lab, where we estimated a wavelength, calculated a frequency, used that frequency to calculate the energy. That's one way to figure out how much energy is being transmitted. Another simpler way would be if you knew the energy levels if you knew the amount of energy of each energy level, you could just subtract them. That'll be the energy of the light emitted. And there's one more way, and it's kind of a scary equation, but it's really not that bad, called the Rydberg equation. And the Rydberg equation looks like this. 1 over lambda, so this is going to allow us to calculate the wavelength of light, is equal to the Rydberg constant times 1 over the energy of the lower energy level squared minus 1 over the number of the higher energy level squared. So if we know what energy levels the electron transitioned between, we can calculate the wavelength of light that we should be able to see. Now, the Rydberg constant that you need in order to solve with this equation is 1 times 10 to the negative 7th meters to the negative 1, or 1 times 10 to the negative 7th over meters. That's another way to look at the unit. 1 times 10 to the negative 7th over meters. And the reason why it's over meters is because our wavelength here is in the denominator. So on this side of the equation, I'm going to need my length measurement or unit in the denominator. Okay, so let's do the practice problem from your packet. The practice problem says, calculate the wavelength for the spectral line that we are going to see when the electron transitions from the 4th energy level down to the 2nd energy level. So it's telling us the transition happened between n equals 2 and n equals 4. So it's dropping from the 4th to the 2nd. So all we have to do is a little bit of algebra, which I know can sometimes be a struggle for some of us. So plug in that constant, 1 times 10 to the negative 7th over meters, 1 over the lower energy level squared, so that would be 2, minus 1 over the higher energy level. Where did that electron start out at? Started off at the 4th energy level squared. Okay, so 1 over lambda is equal to 1.0 times 10 to the negative 7th over meters times, all right, you guys should be calculating here along with me. So 1/4 minus 1/16. Let's go ahead and work in decimals, not fractions. So I get 0.1875. I need to multiply that times my constant. And I get 1 over lambda equals 1.9 times 10 to the negative. Oh, I got to count all these zeros. 1, 2, 3, 4, 5, 6, 7, 8. Negative 8th. And again, this is over meters or meters to the negative 1. So now I need to solve for lambda, right? Right now, lambda's in the denominator. I need to get lambda out of the denominator. So I'm going to multiply this side by lambda, and I'm going to multiply this side by lambda. So that's gone. I'm left with a 1 on this side. So this number times lambda equals 1. How do I solve for lambda? Divide both sides by 1.9 times 10 to the negative 8th. Oops, my pen is going crazy. So lambda is going to be equal to 1 divided by 1.9 times 10 to the negative 8th over meters. So my inverse, 1 divided by this answer, equals 5.3 times 10 to the 1, 2, 3, 4, 5, 6, 7th. Uh-oh, my child is yelling at me. Hang on, I'm gonna pause. Oh, can I pause my recording? Hang on, Parker. He left. Okay, so I get 5.3 times 10 to the 7th. This does not seem right. I really feel like I screwed something up, you guys. This seems totally wrong. Am I using the wrong constant? Oh yeah, I'm using the wrong constant. I don't want to re-record this whole video. I'm not going to. Okay. Look, teachers make mistakes. I knew that answer didn't make any sense. You guys, this constant is not to the negative 7th. Ugh, it's to the 7th. 1 times 10 to the 7th, not negative 7th. Ugh. 1 times 10 to the 7th meters to the negative 1. Okay, look, make this positive. Boom, positive. Boom, positive. Okay, so that should be to the positive 8th, right? 0.1875 times 1, 2, 3, 4, 5. Oh, nope. 1, 2, 3, 4, 5, 6. Okay, so here's where everything changes. All right, this number times 1 times 10 to the positive 7th is equal to, so we'll go over here, 1 over lambda is now equal to 1.875, or 1.9, times 10 to the 1, 2, 3, 4, 5, 6. There we go. And this is again over meters. So to solve for lambda, and multiply by lambda on both sides. So essentially to solve for this, it's going to be 1 divided by that number, or the inverse. And I get the number I was looking for. 5.3 times 10 to the negative 1, 2, 3, 4, 5, 6, 7, negative 7th meters, right? Because if we're dividing by meters to the negative 1, that's going to give me meters. All right, hopefully you guys aren't too confused. Convert this to nanometers. 1 meter, 1 times 10 to the 9th nanometers gives me 530 nanometers, which makes sense. This would be like a blue colored light that we would see when the electron drops down from the 4th energy level to the 2nd energy level. All right, sorry about that, you guys. See, we all have algebra issues sometimes. I guess it really wasn't an algebra issue. It was a use the right exponent in your constant, Ms. Herrera, issue. Okay, so 3 different ways that we can calculate the colors of light that we're going to see when electrons transition between energy levels. However, we did all of that work, right? We did all of this work explaining with this Bohr model of the atom why we're seeing these different colors of light as electrons transition between those energy levels. And it turns out that this explanation that Bohr had only really works for hydrogen. That Rydberg equation that we just used is able to predict the wavelengths of light when there's just one electron transitioning between those energy levels for hydrogen. But remember, those energy levels are different for different elements. So the math falls apart. Like the math doesn't work out. We can't predict the colors using the Rydberg equation for helium or for neon or for sodium or for any of the other elements. So that's a problem, right? And so the Bohr model has some limitations. And that first limitation is that the math predicting wavelengths based on electron transitions only worked for hydrogen. Oops. Second problem is this model could not explain bonding. If we relegate electrons to these set circular orbits, it's very hard to explain how it is that electrons transition between elements for ionic bonding, or how electrons can be shared between elements for covalent bonding. And then lastly, it turns out that electrons don't actually exist in set circular orbits. In fact, electrons are constantly moving, and they are moving as waves. And so we can't put them in these discrete set circular orbits, as Bohr did. So you're like, why did you just make me listen to that whole lecture? Well, the idea that electrons have certain amounts of energy and that electrons exist in energy levels, like we were saying up here, electrons existing in specific energy levels, that is still correct, okay? So the idea that Bohr had about electrons having energy and electrons being able to transmit energy, that's all still correct. In fact, the energy levels are still numbered, N1, N2, N3. They're just not these set circular two-dimensional orbits It's a little bit more complicated than that. And we are going to talk about that all together in a lecture in the coming days. So I hope you enjoyed the flame test lab. I hope this conversation about the Bohr model helps you better understand what it is that you were seeing. And then we're going to further complicate matters with our final model of the atom called the quantum mechanical model of the atom. And I promise you that that's the last one. All right, good job. I'm sorry for the messy algebra. And I will see you guys in class.